In this problem, we'll introduce the idea of an arithmetic gradient. Pause the video, read the question, and when you're ready to see the solution, restart the video. So in this problem, we're given a scenario where the owner of a car would like to set aside money today in order to be able to pay for all of the future maintenance costs of his car. Now, in reality, hardly anyone ever does that, but let's just suspend judgment for a moment and take this for what it is as an engineering economics problem. So we'll be approaching it the same way that we do most of our other problems. I like to start every problem with a cash flow diagram. So in this problem, we're told that the owner of the car would like to cover the payments for 5 years of maintenance. So the question is, how much money today, in other words, what value of P does he need to deposit into a bank account in order to be able to pay out these expenses? And you can see in the problem that these expenses seem to follow a bit of a pattern, where the expenses that are anticipated in year 1 are $120. In year 2, $150, year 3, $180, year 4, $210, and in year 5, $240. So you'll notice that they sort of increase at this constant rate over time, and that might be typical for many pieces of equipment that we'll encounter in engineering economics problems. This particular one is a car, so you can imagine as the car gets older, we need to spend more money on maintenance. So again, the concept of equivalence is really what we're interested in. What value of money today is equivalent to these future payments over the next 5 years, given the particular interest rate? So the first thing I'd like to do is help you to identify the patterns that are useful for engineering economics calculations. And this problem, we should immediately recognize, can be broken into 2 parts. So I have one part that would be, let's say, the constant payments of $120. And you would probably agree that there's $120 paid in each of these time periods, plus a variable amount. The variable amount goes up by the same amount each month, and that's a clue that we use this tool called an arithmetic gradient. We don't have to do too detailed a calculation to realize that, in fact, that increasing amount is $30. And we call that G. So in this particular case, we have an underlying annuity of $120 per year. And then on top of that, we have a gradient of $30 per year. So how do we calculate the P, given the fact that we've identified these two patterns? So what I'd like to do is just show this graphically, that I'll maybe make them just a little bit smaller, because I'll draw a couple, 1, 2, 3, 4, 5. So here's my 5 years, my unknown P, and I'll just put the $120 annuity on here. And I'm going to call this P1. My $120 underlying annuity plus the gradient, draw the gradient, 1, 2, 3, 4, 5. The gradient amount will be 30, 60, 90, 120. Looks like this, where the G is equal to 30. Please take note that at the time t equal to 1, the value of that extra payment is actually 0. And in fact, this is the pattern of payments that fits the formula for an arithmetic gradient. So very important to note the first time period in our time series actually has a value of 0. Sometimes this is described as 0g. This is 1g, 2g, 3g, and 4g. Some books will describe it that way, and in fact that's quite accurate. But just remember that the counting starts at time t equal to 1 with a multiple of 0 times the value of g. Well, it's not too difficult for us. Oh, I shouldn't forget that we also have something over here called P2, and I'll say that P1 plus P2 will be equal to the actual P that we're looking for in the problem. We've already done problems like this, where I can calculate the value of P here quite easily, where P will be the value of the annuity times the P given A, I, N. Quite simple for me at this point in the course to be able to calculate P. But what do I do over here? Well, one of the things that I can identify from my engineering economics textbook is that I have a way to convert this gradient into an equivalent annuity. Okay, so imagine for a minute that I take this same amount, these same dollar amounts, and I'll run them through a formula that will convert them into some equivalent constant amount. And the way that I do that is with a factor that we call the A given G factor. So in order to do that for this problem, I can calculate the value of this new value of A. Maybe I'll call this A2, and I'll call this 120 A1. I can calculate the value of A2 by saying that by using the A given G factor for I and N times G is equal to A2. So what I've done here is use the A given G factor to convert the G into an equivalent A. Once I have that equivalent A, I then just can simply do the same as I did over here, where, sorry, that should be P1, where now I can say that P2 is going to be equal to the value of A2, or the value of A2 is actually this expression, so I'm going to write G times A given G I N, right? So this is really my value of A2, times the same factor I used over here to convert the A into the P. So here I have the P given A, I, N factor, and these will be the same factor. So the one thing I didn't mention here is that the value of N for all of these problems is 5. Don't be confused by the fact that we actually don't have a payment here for the G. Remember that the pattern for recognizing a G has a 0 here, but that still counts. So in this timeline, we still have N equal to 5. And N is equal to 5 for each of these scenarios. So we were also told in the problem that the I was equal to 5%, and that was 5% compounded annually. So if I go ahead and work out what these values are, my P1 is going to be equal to the underlying annuity, the 120, times the P given A, I, N factor for 5% and 5 periods, which is equal to 120 times 4.3295. Check that you can get that value from your compound interest tables. So my value for P1 should be $519.54. Over here, my value for P2 will be equal to the value of G, which is 30, times the A given G I N factor, which is 1.9025. And before I write the next factor in, I'll just take note that, in fact, if I was interested to know what is the value of an equivalent annuity for this particular series where this is 30, 60, 90, 120, what I can do here is say, well, this part is really the value of A2, and just for your interest, that's about $57. So this equivalent annuity is $57 of constant payments. And then my next job to convert the $57 constant payments to my P2, I actually use the same factor I used over here. So 4.3295. If I work out what that is, I get $247.11. So remember back here, I split the problem into two, solved for a P1 and a P2. So I come back here to my original problem and say, well, what was the value of P? P will be the value of P1 plus P2. So for this problem, it's simply 519.54 plus 247.11, or $766.65. So this is the amount of money the car owner needs to put in the bank account at time t equal to 0 in order to be able to cover all of these future maintenance payments on the car.